Hey, what's up, guys? So today we're gonna be digging more into the natural frequencies and mode, try to understand them a bit, try to know how to actually use them when designing something, and we're gonna be talking about how to define them in a first degree of freedom, and then go into maybe multiple degrees of freedom and understand how to define those natural frequencies and modes and such. Okay, so first thing I want to talk about actually is what are natural frequencies. So natural frequency is the frequency at which your system is replying only based on stiffness and mass. So it's a characteristic operational frequency of oscillation or movement. I don't want to say movement, but let's just say of oscillation for your system. It's very characteristic, and we have two types of system, right? We have continuous systems, which we haven't talked about. I think next video is going to be starting into continuous systems, but in this video we're still talking non-continuous systems. We're still talking rigid bodies, non-flexible bodies, right? Because rigid bodies have a way where we can control our degrees of freedom, and so your natural frequencies will be equal to the degrees of freedom. Think of it as you're having one natural frequency per degree of freedom. Not only that, but your natural frequency is going to be one natural frequency per degree of freedom, and then you're going to have a vector of modes, right? So a whole mode for the whole system at that natural frequency. So basically what I'm trying to reach at is for non-continuous systems, especially linear vibrations, for rigid bodies and such, you would expect to have n degrees of freedom, okay, which equals to n natural frequencies, which equals to n modes of vibrations. Okay. All right. So let's talk a system like this, right, where you have some force acting here and some x acting here. We've already talked about the equation of motion for the system, and it should be memorized by now, which is mx double dot plus cx dot plus kx equal to some f, right? And we've also talked that a good solution for these equations will be maybe x equal to x naught e to the I omega t, and then for f it's going to equal to the same thing, f naught e to I omega t. And we've described a little briefly on the e part. We're only interested in the real parts, so the imaginary mainly hold phase information and such. We're mainly interested about the real magnitude of it, or the real parts of it, and that's the part that's actually is being realized. So let's talk a little bit here of complex identities that we need to know in order to go through these problems. Okay, the first identity is actually Euler's rule, which is e to the I of theta is going to equal to cosine of theta plus I sine of theta. Okay, so this rule is very important, and it will pop up a lot, right? And usually we see that this is my real and this is my imaginary. Okay, so this is very important, and it will pop up a lot. Another identity that is really cool for us to know is C E I theta is equal to square root of, I think, actually no, not square root, yeah, A plus BI. That's another very important identity. So think of this, right? Think of this. So you have you have a number line, right, where you have some imaginary section and real section, and you have some point A and B here, okay? So that point, this is your vector going to that point, right? You have some theta here, and that's what that theta is, right? And this here is your C. So another way to write your C is C equal to square root of A squared plus B squared. Again, these are all very important identities that, you know, for complex numbers, we're going to be dealing with a lot, right? So another way to look at this, right, is get that angle. So that angle will be the arctan, right, of my imaginary versus real. So that will be my B over A. Again, this is important. This is important. This is very, very, very important. And this is important. Okay. So those identities will help us go through equations like this and maybe help us, I don't know, simplify vibration design or solutions, right? Because that's ultimately why we're understanding this. We're understanding this because we're having some problematic mode or some problematic frequency or, you know, natural frequency that we are trying to deal with, right? So let's go through this. So let's plug in our solutions. So I know that my x dot here is equal to x naught I omega e power I omega t, and my x double dot is equal to x naught omega square minus e the I omega t. So right away I can capture that my x naught e omega t is not going anywhere, right? Hence all the Laplace transformations built on, but that's for a different topic. All right, so let's substitute in, right? So let me take that part out right away. This way I try to keep that video somewhat short. I know I promised 10 minutes, but I'm not delivering. And let's write what's inside. So I have minus m omega squared inside. I have plus I omega c, and I also have plus k, just k, equal to f naught e I omega t. So this is amazing because now I got, you know, some attempt at the solution. So I can now find the roots of the equation. But before I do that, right, let's try to find a relationship between the input and the output. So we have, you know, some transfer function here that I can put in some output, some input force, right? And I can get some displacement. So how about we get that transfer function? Okay, we'll call that transfer function t. So my transfer function is going to be x naught, right, over f, which is going to equal to t, which is going to equal to basically 1 over negative m omega squared plus I omega c plus k. So that's my transfer function right there. Okay. Okay. Well, I'm looking at my transfer function and it's not really helping me solve it any better. Okay, well, we know a couple of things that we would like to substitute in, right? So first of all, I want to relate everything is happening here to the natural frequency. So we already know that natural frequency is equal to square root of k over m. So maybe this is number one thing we're going to sub. Number two thing we're going to sub is, okay, well, I also know that my system would have some type of damping, right? Or, you know, there's some damping, and I know not some damping in the system, but damping, you know, has an expression that I know about, and there is a C here, so there is some type of damping happening. So maybe we can, you know, relate that as well. So that here will be C over 2 omega n m. Okay, I know I got that wrong last time, so I think I corrected that, but anyway. So that being said, let's sub both of those into this here, and let's see what we come up with, okay? So what we come up with, I have it written down here, this way I save myself some math. and it's going to be 1 over k, right? 1 minus omega squared over omega n squared, okay, plus I 2 zeta omega over omega n. Okay, so let me take a step back and look at this. So this looks very, very familiar. As a matter of fact, this looks like I can just write 1 over k times 1 over a plus bi, right? And, oh, whoops, that's a complex identity. Well, that's great. So now I can identify a as 1 minus omega squared over omega n squared, and b as my 2 zeta omega over omega n. So that's awesome. All right, well, what can I do from here? So this is where I reached. Where do I go? Well, the first thing I want to do is I want to get rid of that I at the bottom. So what I'm going to do here is I'm going to multiply with the conjugate. It's the oldest trick in the book to get rid of complex somewhere. All right. So that being said, I do get some 1 over k, right? Up here I get a minus, or let's say plus minus I b, right? I'm writing it like that for a reason. Divided by a squared plus b squared. Great. So I know that this here can be written in this form. So I can write this as 1 over k times, now I know that my c is equal to the square root of a squared plus b squared, right? So that can cancel with that, and I will be left here with a square root of a squared plus b squared. And up top here, I will be left with some e negative I theta. Okay, so this is where we are. Actually, let me take theta out and let me write phi. This way we don't confuse stuff. Okay, so I've reached here. Where's my next step? Well, so let's take this. Okay, let's take this and write it here. So I have my x naught over f is equal to t, right, my transfer function, which is equal to, where is it? So I have 1 over k times square root of a squared plus b squared, right, and then 1, where a is equal to, if I remember right, omega n squared squared, and b is equal to, again, if I remember right, 2 zeta omega over omega n. Am I right? I am right. Okay. Awesome. And that's all time e for negative I phi. Okay. So if I obviously see here that I have some real, so I have some real part here, and I have some imaginary part here. Well, my imaginary part is great to convey phase, right? So this conveys, this would be awesome for me to compute phase out of. But this here is the one that would help me, the magnitude, right? So this is the magnitude of my transfer function. So you might ask me, hey, why are we doing this? That's a great question. So what if I told you that now I can have a relationship between input and output based on the frequency ratio between my operational frequency and my natural frequency of the system, right? And also I can understand its relationship with the damping, and I would have a beautiful graph like this. This is a star right there. So a beautiful graph like this that will help me identify how to get out of my problem. For example, let's say I want 0.2% of whatever vibrations happening input to be translated to my output. Okay, well, 0.2 is somewhere here, right? So if I know that my 0.2 is somewhere here, right? Is it worth it at all for me to do anything with the damping? I mean, you can see that I want to be in this side of the graph, right? I want to be in this side of the graph. I call this the good side, right? So I want to be in this side of the graph. That being said, my damping, I mean, you can see how close it is. It does not, based on what I'm seeing here, it doesn't really help me. Okay, so what does help me? Well, it looks at what helps me here is my omega n. So my ratio is equal to omega over omega n. So if I were to play with this, right, because I know that my omega n is equal to square root of k over m. So if I want to make this number bigger, I make my omega n smaller, right? Which means I can come here and either increase the stiffness or decrease the mass, right? So this is just a quick solution right away for me to play with it, and I know right away that my damping is not going to affect me. Okay, well, you might come and ask me, so what is damping good for? What am I doing with damping here? Well, damping is very important because damping is helping us get through this resonance. This is bad, right? I mean, look at how much amplification happened through this area, which means if you don't have enough damping and you went through this area, you're gonna fly, right? And it's gonna be hard for us to pull that to, hold that vibration down. Or that's my analogy, but basically it's gonna be hard for us to control that vibration. So again, this is really cool, and this is such a quick thing that you can know from this originally planned 10 minutes, maybe a little more than that video, and it could help us, save. It can help us create some solutions right away just by knowing this graph and how to deal with our transfer functions and such. Okay, so this is great. So we've covered that part, so that's, vibration isolation and such. Now let's go into solving vibrations, right? Oh, something I forgot to mention. This can only happen in steady state. Now, to understand why, wait till we reach classical controls. But this has to happen in steady state where you don't have other things getting involved. So all of this it has to be steady state. That's important. Okay? All right. Well, let's move on to something else. So we've talked about natural frequencies. We said, okay, I can probably get my natural frequency. So I can just go solve for my natural frequency, right? So over here, we didn't really need to solve for the mode, right? So we solved for the natural frequency, but we didn't really need the modes, right? Again, it's also because it's a 1 degree of freedom, but we didn't need the modes, right? So let's go here and let's discuss something else. Let's discuss a system. So I have some degree of freedom system, okay? Now, for me to be able to explain that system, I'm going to write my equation of motion. But this time, I don't have one equation of motion. I have equations of motions. So how am I going to write this? Well, I'm going to write that in terms of m, right? X double dot plus c x dot plus k x equal to sum f. Okay. Now I'm talking about my mass, damping, and stiffness in my whole system, right? So you would expect this to look something like, actually let me give an example here, right? So if I have, again, I'm just gonna write some equation. So m1 x double dot plus c1 x dot x1, yeah, plus x dot 1 plus k2 plus k1, you know, x1 equal to 0, and then m2 x2 double dot plus c2 x2 dot plus k2 plus k1. Wow, that's kind of counterintuitive. Let's just say k2, right? x2 equal to 0. So something like this, for example, would be a 2 by 2 matrix, right? So it's going to be degrees of freedom by degrees of freedom, where I would come here and, you know, I have my x1 double dot and x2 double dot, and I would come and say, okay, so I have m1 and I have 0, and here I have 0 and m2 and m plus, and I would do the same for the thing. Okay, so a generalized statement for me to write this, right, is to write m x double dot plus c x dot plus k x equal to f, right, or f. Okay, well, if I want to generalize this even more like from a solution perspective, I'm going to come and say, okay, my x is equal to an a cosine of omega, some omega, right? So I'm going to call this omega. So I'm going to call this for, because obviously, like I said, we're going to have one natural frequency per mode, and we're going to have, per degree of freedom, and one mode per degree of freedom as well. Well, per natural frequency. So we can say, okay, so my xn is equal to an, right? So this is my vectors at that mode, cosine omega n, right? T plus some phi n. Okay? So this here is a generalized expression, right? Where I can just go in and say, this is my solution for each, you know, this is my possible solutions out there. Now we'll talk a little bit here about my superimposition, right? But if I held this here and I came to say, okay, so what's my x dot of n, right? So again, we'll treat it the same way like we've done. So we're gonna be my omega. Let's see, it's going to be my omega an cosine of omega n t plus phi, right? Minus, I think. So that's for my, is it minus cosine, sine? Yeah, I think so. I might be wrong, correct me if I'm wrong. Is equal to negative omega squared. No, I think it's positive. Negative omega squared an cosine of omega n t plus phi. All right. What am I trying to reach at here? So forget about the n here. Right. So what am I trying to reach at? What I'm trying to reach at is, if I were to sub this back in here, right, I'll end up with, again, a common term, right? Actually, all of this is a common term. And then I would have an equation looking like this. Negative, again, this is me trying to find my natural frequencies. And the definition of natural frequencies is that I push this guy to 0 and I push this guy to 0. I disregard those two, right? So in this case, I get my negative m, right, x double dot plus my K matrix, right, which now basically doesn't have an X. This actually also, I'm not sure why I wrote it this way, it's omega squared, right, it's from here, because I substituted a solution for X, plus my K equal to 0. Okay. So now over here, I have a matrix, right? And a matrix. So what I come and say here, well, it's obviously going to be some multiplied by some A, right? Which is my vector for my mode vector, right? But as of right now, I don't care about this. And when I equate this to 0, the modes can't be 0, because if the modes are 0, then what am I doing solving this equation, right? So if that's the case, then I can easily obtain my natural frequencies by taking the determinant of this, right? So the determinant of this will give me my, like when I equate it to natural 0, I get my natural frequencies. So that's how I get my natural frequencies. Okay, well, now that I have my natural frequencies, what do? Well, you plug them back in and you start solving for the eigen, for the, how do I say this? You plug them back in and you start solving for your eigen vectors, which are your modes. I apologize, I kind of zoned out for a second. Okay, so if I were to come here and multiply this by the inverse, right? So I would have, this is the same identity that we have here, so this equation here. So if I were to write this equation again, so minus omega squared m, right, my matrix m, times my modes, my vector, right, my eigenvector, plus, or let's just call it modes for now. So this is my modes coefficient plus k times my modes as well, equal to 0. Again, I'm solving it. I'm putting in my natural frequencies in here, right? I can do this. I can multiply both of them by the inverse. And when that happens, now a matrix by its inverse gives you the identity matrix, right? I think so. And then you're going to have that term here, which you can call A. Okay, so a matrix by its inverse, right, multiplied by a vector, so that will give us here, a vector, right? So if I were to write this in a different way, I would write this as my A matrix, which is this one here. A is equal to my Eigen Values. Sorry. And then from here, I basically got my eigenvectors. I just have to solve for my eigenvectors. Okay, so it sounds simple enough, and to be honest, it is going to be amazing for you to do this on MATLAB. Matter of fact, I've actually prepared an example on MATLAB that I will show you here in a second, but I want to talk about something else here, which is when you have modes and natural frequencies happening, so when you have multiple solutions of X, like, multiple modes happening, mode shapes happening, what you do is that you are adding them all together. So that's called the superposition theory, right? Where they're all happening on the top of each other. So you can destruct your modal, right, into a into its modals superimposed together. So another way I want to write this is X, which is the solution that we just came up with, is going to equal to U Q of t. Okay, so you can say U1 Qt of 1 plus U2 Qt of 2 plus 2 un qt of n. Okay, degrees of freedom. So this here, a lot of people, this is all of your natural modes together. So that's your natural modes multiplied by your matrix, okay, your U matrix. Okay, so let's solve with this here. So let's say I have some x as a solution. My x is equal to U Q T. Okay, so my x dot is going to equal to U Q dot T, and my x double dot is going to equal to U Q double dot T, right? I think they call this the modal coordinate. It's the same thing we derived in the other slide here. This here. So we're doing the same thing. All right. So now that I can write this, I can write my m u times q double dot, right, plus my cu q double dot plus ku, not double dot, plus ku q equal to u times f, which they call, actually there's no u here, equal to f, right? So that being said, let me go ahead and pre-multiply all of them by the transpose of that matrix U. So when that happens, I get those matrices here. And those matrices here are called the diagonal, because ut times u gives you a diagonal matrix, right? When you multiply the transpose by the u, it gives you a diagonal matrix. So you get your diagonal mass matrix and your diagonal stiffness matrix and your diagonal dampening matrix. Okay? All right. So what am I trying to reach at? Why am I doing all of this? Right? Because you can call this your M, I'm just going to call a name. So I'm going to call this MR, I'm going to call this CR, I'm going to call this KR, and I'm going to multiply here by UT as well, and that's called Q of T. And that's the modal force. The modal matrix force, I think they call it. All right. Now, why am I going through all of that? Well, I'll show you here in a second. When you reach this, right, you can easily start to decouple your system. That's what we're trying to do here. We're trying to isolate the different modes and the different frequencies from each other so that we can better analyze our system. Okay, so if I were to come here to my MATLAB script, let's see, where's my MATLAB? So if I were to come here to my MATLAB script, okay, I've already been running a MATLAB, and basically what it is a 2-degree of freedom system. I can make it more than that, and I've defined my masses, defined my springs, defined my dampening, right? And I basically put them in matrices. I inverse the M, because that's, we said we needed to do that on the last slide, right? Because when I inverse the M, I can get my A matrix. And when I take the eigenvalue of the A matrix, I get, like when I take the determinant of the A matrix, I get my omega n's, right? And when I take the eigenvectors of the A matrix, right, I should get A, if you know, so if I have two natural frequencies, how big is the matrix that I should be getting for the eigenvectors. Well, if that's the case, I think I call the matrix U. I should be getting 2 by 2. Why? Because I have 2 modes for each well, I have one mode for each. I have one vector of modes for each frequency. And that's really what's happening here. That's why I got a matrix that's 2 by 2. It's going to be n by n, right? Okay. So again, just putting them in matrices, get my eigenvalue, and then I come here and my U being the so this is my U. Okay, so the U that I have here is that U, and this U is my eigenvectors. Okay, so that's my matrix of eigenvectors. That's what that is. Okay, let's go back here. All right, so now I need to calculate those guys, right? I call them M of R. So my diagonalized mass matrix, right? And my diagonalized stiffness matrix. This here is a little more complicated, and I'll explain why. And there's like a trick around it. But my diagonalized mass matrix and my diagonalized stiffness matrix are the ones that I wanted to calculate. Now, why would I do that, right? Is because you can check right away and you can just, basically you've decoupled your system. So if I were to do this, right? If I were to look at my MR here, oh, sorry. If I were to look at my MR here, right? And if I were to look at my KR here, and if I were to take the first value in MR, do you see how it's a diagonal matrix, by the way? So if I were to take the first value of MR, so I have my omega n is equal to the square root of KR, right? And in this case, I'm only going to be taking the first value divided by MR, and that should give me what? So if I am correct, and I truly decouple the system, that should give me my natural frequency, right? So if I were to, that's a big number. Did I do this? Oh, I didn't do this right. So this is my natural frequency, and this is my eigenvalues, which makes sense, right? My first natural frequency is the same. So this is a really cool check of us. So it's a really cool way for us to decouple the system. Now it doesn't work that cool with this guy here. Why? Because the C matrix is complicated. So there is a lot of ways for us to, how do I say this? To estimate the C matrix, okay? Again, it depends because it's ideal, and in our world, to be honest, it's never ideal. So there is something called, and I'm going to talk over this briefly, right? Raleigh's method. I think it's right. Raleigh's method, Raleigh's equation, damping method, or model. Really bad with it. And basically what it is that I come in here and I say, okay, well, how about if I break my model and say that my C, my CR here is going to equal to some alpha value of MR plus some beta value of my KR. So when I come and do this, right, it helps me decouple the system by saying, okay, let me put in some of my experimental data, and let's see how my how my frequencies will come back. And based on that, I can start putting them here, and I can start making some, estimations on what do I think my frequency is. Or I can solve, let's say I have two frequencies. As long as I have my initial conditions and such, I can actually solve those frequencies and see, how am I looking? Can I decouple the damping? If everything is good, if I have an ideal viscous damping, I should be able to decouple it. If I don't have that, then it might get a lot harder than this. So just to recap here, right? So we've talked about isolation, vibration isolation, and the method to do that. And it's a very simple method that only applies to steady state linear models that are of finite degrees of freedom. Okay, and from there we talked about, okay, so what if I have n degrees of freedom that I can't possibly write it down one by one. So you can start putting matrices, and MATLAB is great for that because it can just solve it for you. And from there you can get your Eigen Values, which are your natural frequencies, and your natural frequencies are the oscillation of the systems that wants to happen at their degrees of freedom, at their respective degrees of freedoms. And then you're going to have your eigenvectors, and that's the unforced, undamped natural frequencies. And then your eigenvectors are going to be your modes that, your eigenvectors are going to be the mode vectors that are happening at each natural frequency. And you always expect them to be a matrix of degrees of freedom times natural frequencies. Since natural frequencies are degrees of freedom, so degrees of freedom times degrees of freedom. So it's always going to be a square matrix. And then using some linear algebra manipulation, right, which, to be honest, best done in MATLAB. It comes back with a solution that we can actually use to, again, manipulate it via linear algebra to be able to decouple the system and be able to, solve for my damping and such, to be able to model the system or understand the modeling of the system.